Welcome back. In the last video, we completed our discussion about cyclotomic extensions, and the topic now is the final topic of the course. So, the rest of the course is going to focus on solving polynomials by radicals. So, in the very first video, I described what we mean by this. So, let me quickly recall that, and then we formally will define what this means. Okay. So, we can generally define, I am now going to stick to characteristic 0 fields for the rest of the course. For simplicity, some of these statements will be true in most characteristics, but I want to stick to complex numbers because it is easiest to state it without any restrictions about characteristic. Let us take a complex number. We say that, so I do not want to formally define as of now, but a complex number alpha is expressible by radicals. So, I have to fix a base field. Okay. So, it is expressible by radicals over some field. So, C contains F, and we typically take F to be Q. If alpha can be expressed, so this is not a formal definition, that will come in a minute, but I want to indicate what we need, can be expressed using elements of F by the operations, of course, the standard operations, addition, subtraction, multiplication, division, and radicals, taking radicals. Okay. So, for example, root minus 1 is one such, 3 plus 2 times minus 2 by 5, or 10 times 5th root of 8 plus 6th root of 10 plus 100th root of minus 8 by 25th root, 25 times 10th root of 2. I mean, I am just, as you can see, just randomly writing some numbers. Okay. These are expressible by radicals. Over Q, in fact, because each of these numbers is an expression involving rational numbers and the 5 operations, addition, subtraction, multiplication, division, and you are allowed to take radicals. That means taking roots of elements. So, you can take 10th root, a 5th root, and so on. So, this is roughly what it means to be, I mean, this is loosely speaking the definition of being expressible by radicals. But in order to give a formal definition, and we will use field theory for this, I am going to define a series of statements here, give you a series of definitions. Okay. Let K over, okay, so basically I will fix be a field extension and fix an element in the bigger field. Okay. So, the first definition is that. So, these are crucial definitions. So, as I said, I want to formalize this notion that I am trying to define here, what it means for something to be expressible by radicals. So, I need to say that there is a tower of extensions from starting with F all the way to some field containing alpha, where each extension is a radical extension. So, that is going to be our formal definition. So, but in order to do that, let me give you these definitions. Is simple radical. So, this is the terminology. The extension is a simple radical extension if K equals F alpha. Okay. So, let me not fix alpha here. So, I am starting with an arbitrary field extension. If K equal to F alpha such that alpha power n equals is in F for some positive integer n. Okay. So, essentially what we are saying is that so K is obtained from F by adding a or adjoining, that is the correct term, a radical, by adjoining a radical. Okay. So, this is a simple radical extension. A trivial example, we will do more examples later, but okay. So, this is a simple radical extension. You are adjoining an nth root in general. Here you are adjoining a square root. So, or you are they are all simple radical. Okay. So, now a radical extension is one which consists of a tower of simple radical extensions. K over F is a radical extension. So, I removed the word simple here. If there is a tower of field extensions, so this is the following, but so I am going to write it like this: F equals F0 contained in F1, contained in F2, all the way up to Fr, which is K. Okay. So, our usual way of denoting this is, I just did this to save space, but right, this is our usual way of describing such a tower, such that each of these extensions is simple radical. Okay. So, K over F need not be simple radical, but it is made up of simple radical extensions. Okay. So, we will do examples of all of these things. So, now let alpha be in K. So, K over F is a fixed field extension a priori. We say alpha is solvable by radicals Okay, so let me erase this, I will write it smaller. So, Fr is K, Fr minus 1, F1, F0 which is F, and this is simple radical. So, that is my short for simple. SR is simple radical, each of them is simple radical. So, now let us come back to the third definition. Alpha in K is said to be solvable by radicals or simply solvable. Often we will just use the word solvable because we will only talk about solvable by radicals. If there exists a radical extension, I am not saying K over F is a radical extension, I am only saying that there is a radical extension L over F such that alpha is in L. Okay. So, I am not, a priori you are given K over F, alpha is here, but then you can construct a tower like this containing alpha, and this is simple radical, this is simple radical, this is simple radical. Okay. So, this is the meaning of being solvable by radicals, and I will let you think about this. This is exactly the informal definition we recalled earlier, right? Informal definition being this. This is something for you to ponder, but if alpha is in L and each of these is a simple radical extension, then it will become a very messy expression, of course, depending on how many fields are in this tower. Nevertheless, it is possible to express alpha with starting with elements of F and using only radicals and of course, the usual 4 operations, because if you have, let us say, 2 things. So, as I said, I will not, let us say alpha n is in F and beta m is in F alpha. This is simple radical and this is simple radical. Okay. So, I am not giving you a formal definition, but just to indicate it. And now if you take some a in here, a can be written using a can be written as a polynomial in f alpha beta, where f has coefficients in capital F. By definition, that is the meaning, right? And alpha is nth root of something in f, let us say a1, and beta is an mth root of something in f alpha. Okay, so now you can further write b1 as a function, as a polynomial in alpha, and each of those has coefficients in f, and alpha is already an nth root, so that ultimately anything can be expressed using starting with elements of f and using only radicals. Okay, so I am sorry, I sort of did not explain this in detail, but this is the crucial definition that we are going to take for our informal earlier definition will be formalized by this third statement. And finally, I will give you the meaning of an extension being solvable. K over f is solvable if every element of K is solvable over f. Okay, so I should really write here solvable over f, that is part of this over f. Okay, so it's important to put that over f statement. Because solvability is a property over once you fix the base field, because if you change the base field, something may be solvable or not. So, for example, I mean you can take so pi for example is not even algebraic over q. So, whereas it is solvable over, I mean it is a simple example, but not over q, right. So, it is not over q because it is not even algebraic. So, I really should take an algebraic extension, but I am going to even assume that it is a finite extension for the last part at least. So, for 3 and 4, for 3 I assume alpha is algebraic over f, and for 4 k over f is algebraic. See, if you do not have an algebraic extension, the question of being solvable by radicals does not arise. So, 1 and 2 of course are general statements, but for 3 and 4 you need, for 3 you need alpha to be algebraic, for 4 you need the entire extension to be algebraic. So, let me give you some examples and then we will study this further. So, the question that we want to ask is which complex numbers are solvable over rational numbers, more specifically whether the roots of a given polynomial are solvable by radicals over q. So, you start with a polynomial with rational coefficients, can the roots be expressed using radicals starting with q. So, that is the question. In the new language, our question is, so the question that we want to address is the following. If f is a polynomial with rational coefficients, are the roots of f solvable over q? Okay. So, that is the question that we want to address. This is a question that Galois solved, and he showed that for a degree 5 polynomial you cannot do this. Okay. And the final definition, let me write that here. A polynomial is solvable if all its roots in a splitting field. Of course, capital F itself may not contain the roots. are solvable over F. Okay, so again I omitted the crucial thing here, soluble over F if all its roots in a splitting field are solvable. So the question can be rephrased as follows. So rephrase the question. So the rest of the course is going to be addressing this question. If given a polynomial f in qx, is it solvable? Okay. So we are going to develop the theory as Galois developed to answer this question. Okay. So in order to do that, we need to rephrase radical extension. Before I state that, let me give you examples. Okay. So first example is if okay. So this is the only. I mean here this is very general. Of course, I am assuming characteristic of f is 0. So this condition is no condition, but this statement is true for any field provided its characteristic is different from 2. Any extension k over f of degree 2 is simple radical, is a simple radical extension. Why is that? This is an exercise we did, right, by an earlier exercise. What we did was we selected an element alpha which generates k over f, because you can take any alpha not in f, then you take the irreducible polynomial of alpha, it is a degree 2 polynomial, and you simply notice that if you take the discriminant of that and attach its square root, you get k. Okay. So k is obtained by attaching a square root. So k is f adjoined root delta. So it is a simple radical extension, right? The first definition is an extension is simple radical if it is generated by an element a power of which is back in f. So of course, so delta is the root, so delta square is in f. Okay. So delta is the square root of the discriminant b square minus 4ac. So those are simple radical extension. Any cyclotomic extension is simple radical, obviously, right, because it is generated by a primitive nth root of unity. So that means it is of the forms f zeta, where zeta power n is in f. So this is also clear. What about Kummer extension? So let me state the following. Let f contain a primitive nth root of unity. So here I assume characteristic of f does not divide n. In fact, that is a consequence of this statement, but I did not do that. So I am going to assume this. Again, our main focus will be in characteristic 0, so where this condition is irrelevant. Okay. So let f contain a primitive nth root of unity, where so that is all. So that is the sentence there. Then let k over f be an extension of degree n. Okay. So then k over f is simple radical Okay, so this requires some work. Okay, this much. K over F is a Kummer extension. So, in general, Kummer extensions are simple radical extensions. So, that is what, if it is a Kummer extension, that means K is generated by alpha such that alpha power n is in F, and this of course is if and only if K over F is cyclic. Okay, so we'll prove later something about this. Okay, so this is our crucial observation, that simple radical extensions and cyclic extensions are sort of identical. Okay, I mean one implies the other. I mean, so the extensions that we have studied, namely cyclotomic and Kumar extensions, are simple radical extensions. So let's do one more example. Let's take K to be Q root 2 and root 3 over Q. This is of course a radical extension. Right? This is radical because you can put Q first in Q root 2 and then in Q root 2 root 4. Right? This is degree 2 implies simple radical. Of course, you can immediately see that root 2 power 2 is in Q. This is also because simple radical, because root 3 is the generator of this extension and root 3 whole square is there. Okay, this much is clear. But the claim I want to now prove is that Q over Q root 2 root 3 Q is not a simple radical extension. It is a radical extension of course, because there is a tower of simple radical extensions like this, but it is not generated by a single radical. Why is this? Okay, this is a nice proof. So note K colon Q is 4 of course, that we know because each of these is degree 2. So suppose it is a simple radical extension. Suppose K is Q alpha with for some positive integer. Okay, so this is so I am assuming the contrary. Suppose it is a simple radical extension, that means K is generated by Q alpha with a power of alpha landing in Q. So first note that n is at least 4. Yeah, so it's clear because the irreducible polynomial of alpha over Q has degree equal to 4. That means any polynomial that alpha satisfies has degree at least 4. So if alpha cubed is in Q, for example, this implies alpha satisfies a degree 3 polynomial over Q, right? But that of course can't happen because its least degree polynomial that it satisfies is degree 4. So n is at least 4. And now we bring in some Galois theory here. K over Q is Galois, that we know very well because it is normal, right? Root 2 has all its conjugates there, root 3 has all its conjugates there, namely minus root 2 minus root 3. So it is a normal extension, it is certainly a separable extension, so it is Galois. So that means, in fact, with Galois group, it is irrelevant for us, but it is this, right? So for sigma in the Galois group, that's not identity. What is sigma of alpha? Sigma of alpha must be, okay, so let us take this. Then alpha power 4 n is 1, right? If alpha power n is 1, sigma alpha power n is 1. This means sigma alpha whole power n is 1. So, sorry, so not this is not correct. Alpha power n is in Q. Yeah, so I have to be careful here. So what I really want to say is that sigma alpha power n, sorry, sigma alpha whole power n is sigma alpha power n. This is sigma alpha, this is alpha power n, yeah. So, sorry, so this is what I wanted to say. So, this is because sigma is a homomorphism and this is because alpha n is in Q, and which is the fixed field of this. So, everything, I mean, of course, sigma is a Q automorphism, so it fixes this. So, sigma alpha, so this implies sigma alpha is also an nth root of alpha power n, but then sigma alpha must be something like this, zeta alpha, where zeta is an nth root of alpha power n, because if alpha power n is a, all nth roots of a are alpha, zeta I alpha, where I is equal to, where zeta is okay, or basically I will simply write this. I mean, this is a standard calculation, right? If you get hold of one nth root of a, all other nth roots of a will be simply nth roots of 1 times alpha. Okay? So, this is the reason for, if sigma alpha is also an nth root of alpha power n, which I am calling a, then all other roots of a, nth roots of a are zeta alpha. But now we are in business. So, since k over q is Galois, it is normal. This implies sigma alpha is in k, because it is normal, every conjugate of an element is again in k. That means zeta alpha is in k, but then zeta is in k, because alpha is in k. So, this is because if alpha is in k, you can multiply by alpha inverse, but this is a problem. Because remember, k is in R, k is a real field, because root 2 and root 3 are real fields, but okay. So, what I want to say is that zeta cannot be inside complex numbers, because n is at least 4 and we have to take an nth root of a. So, what I really want to say is that all the nth roots are there. So, I should really add here. So, there is a primitive, okay. So, I am sorry. So, the last point is I am forced to have a non-real nth root of 1, because G consists of 4 elements, right? Right, because G is the degree of this extension. So, G can be thought of as 1, sigma 2, sigma 3, right. So, where sigma 1 changes root 2, let us say sigma 3 changes root 3 and sigma 3 changes both of them. So, then the conjugates of our potential radical element are alpha, of course 1 of alpha, there will be minus alpha, but there will be 2 more. So, maybe zeta, I mean whatever these are. So, alpha 3, alpha 4. So, these must be something like this, where we must have, because the only roots of unity that are in real numbers are 1 and minus 1. So, that is already taken care of here. So, the third and fourth conjugates of alpha must be some complex non-real root of unity times alpha. So that means, and now we use this argument here, because this is in K, so this implies zeta alpha is in K, but zeta is in K, which is in R. So that's your contradiction, right? So I'm sorry I went rather fast about the last part, but this proves that K is not a simple radical extension, because if it were a simple radical extension, if there is a radical element alpha, it will have 4 conjugates, 4 different conjugates. One of them will be a non-real root of unity times alpha, but that will force that non-real root of unity to be in K, but K is a real field, so that is a contradiction. So this shows that this is a radical extension, but it is not a simple radical extension. So let me give you one more example which is exactly similar to this. So let us say F is an irreducible cubic which has 3 real roots. Okay, so we know that it has 3 complex roots and at least one real root, but I am taking an example where all 3 roots are real. So let us take K to be the splitting field of F over Q. Okay, so now I claim that K over Q is not simple radical. We will prove later that it is radical. Okay, so I am going to, I was going to simply say that the proof is exactly similar to this, but let me quickly tell you why it is not simple radical. Maybe in the process this will become more clear to you. So suppose K over Q is simple radical, that means you have this K equals to Q alpha, okay, then such that alpha power n is in Q. Okay, so then what we know is, we know sigma alpha is equal to this for, so let us take the Galois group to be G. We know actually from our analysis earlier that G is either a cyclic group of order 3 or G is S3. So take that, because K over Q is 3 or 6. Okay, so it depends on the polynomial which the polynomial determines which case occurs, but it is either 3 or 6 for a root of unity, right, because for in fact an nth root of unity. This is clear because alpha power n is in Q, so alpha is an nth root of that element. Sigma alpha must also be an nth root of that element. That means the only possibilities are zeta alpha. I claim that there is one of, for at least one, so this is the point that I sort of messed up earlier, but what I want to say is that for some sigma in G, sigma alpha is not alpha and not minus alpha. Why is this? Because this is because sigma, the order of G is at least 3. So you will, I mean, you can say sigma alpha is alpha, sigma alpha is minus alpha for 2 of them, but the third one will be something else, because you are forced to have, I mean, if sigma alpha determines the entire sigma, because K is generated by alpha. So this is because there is at least 3 elements. One element may send alpha to alpha. In fact, one element will send alpha to alpha. The second element may send alpha to minus alpha, but the third will have to send alpha to something else. Then sigma alpha will be zeta alpha for some root of unity which is not in R, right, which is not in R, because the only roots of unity that are in R are 1 and minus 1. So, you are forced to have a different one. But again, as before, by our hypothesis that the polynomial has 3 real roots, we know that k is contained in R. So, this is a problem, because this is in k, this implies zeta is in k. Okay? So, that is a contradiction. Okay? So, this tells you that if you take an irreducible cubic with 3 real roots, its splitting field is not simple radical. It is, however, radical, as we will show later. So, let me just quickly give you an example of a polynomial which has this property. So, is irreducible. You can use Eisenstein criterion here, not directly, but by changing x to x minus 1, and you can also show that it has 3 real roots by just computing some roots and plotting its graph. So, its graph will look like this. So, it will cross x axis in 3 spots. Okay. So, for this polynomial, if you take the splitting field, it is not simple radical. Okay. So, let me stop this video here. In the next video, what we will do is, we will show, for example, that if you take an irreducible cubic, its splitting field will be radical, and more generally we want to understand how to go from radical extensions to cyclic extensions, as I have indicated here. Okay, let me stop this class here. In the next class, we will continue with radical extensions. Thank you.